Hi dear students, welcome to this session. I am your Bala sir. In the last class, we have discussed about the Coulomb's law and how to calculate the force acting between the two charges. And also we have discussed how to find out the force due to the system of charges. Everything we have discussed in the last class. This session is very important session, dear students. So please watch carefully. In this session, we are going to discuss very important properties, very important concepts, particularly about a dipole. And this portion is very essential and very important concept for your board examination. So let's go to the topic. First, we are going to discuss about the electric field. So what is electric field? If we have a charge, doesn't matter it is positive or negative, the space around the charge is generally called the electric field. Okay, so the space around the charge, but we cannot extend the space up to infinity, so that we confine ourselves the space around the charge within which its influence is experienced, right? The charge will exert some force up to certain limit, so that space is called a electric field, generally we say. But if we want to define the electric field, we can define like this. The force experienced by unit charge. Normally we call this charge as test charge. You take one test charge, you place nearby the source charge. If it experiences a force, then we can say up to this point we have the electric field. That is our discussion. Okay. It is defined as the force experienced by a unit charge kept at a point in the space around the point charge. Okay, va? Right. Next, let us consider a point charge, capital Q. Right. It produces an electric field around the charge, point charge Q. Now, we bring a unit positive charge. Normally, we call this as test charge, small q, which is placed at a distance r from the point charge. So definitely it experiences a force which is mathematically given as F is equal to Q into E. Okay, so this is the force experienced by the test charge. Am I right? Okay. According to the Coulomb's law, now we have two charges. One is source charge, that is capital Q, and the another one is test charge, which is small q. Later on we are going to fix this test charge as plus 1 for our convenience. Okay, so there is a force between the two charges, capital Q and small q, and that can be expressed according to the Coulomb's law as F vector is equal to constant 1 by 4 pi epsilon 0 q into q divided by r square into r cap, where r cap is the direction of the force, which is represented by this unit vector. Now, what we have defined for electric field? Electric field E vector is equal to F vector divided by Q. Am I right? Okay. Now, rearrange this expression. Okay. So, how to rearrange this? You just bring this Q here, F divided by Q, and that will give you capital E vector electric field at that point, which is equal to 1 by 4 pi epsilon 0 Q by R square into R cap. So, here this is the expression for our electric field at a point P at a distance r from the point charge capital Q. And just look at the expression E is equal to 1 by 4 pi epsilon 0 Q by R square into R cap. Here the electric field does not depend on the test charge, because in this expression we don't have plus q, small q in this expression, and it is mainly depending on the strength of our source charge capital Q and also distance. Here the electric field is inversely proportional to square of distance. When you come closer to the charge capital Q, closer to the source charge, the field will be very strong. If you go far away from the capital Q, definitely it is evident from the expression, definitely it will decrease to 0 at infinity. Okay. So as I said, this electric field does not depend on the test charge Q. And now look at this graph. Here, how This graph shows how the electric field varies with the distance. So to show this, we take the distance along the x-axis and the corresponding electric field along the y-axis. Am I right? Distance along the x-axis, electric field along the y-axis. So when distance increases, initially when the distance is 0 or very nearer to the source charge capital Q, the field is very strong, is much more high. When the distance increases, the field quickly vanishes, and when you go to the infinity, it becomes 0. So is fastly decreasing, that is depicted in the graph. So which is very important graph for you. So normally in the board exam they will ask you how the electric field and potential. Later on we are going to discuss, students, how the potential, that is also function of distance, that is also will change with respect to the distance. Electric field also changes with respect to the distance. So now you are asked to compare the electric field and potential with respect to the distance. That type of question will come. Now we have shown how the electric field varies with respect to the distance. Now, the direction of the electric field we are going to discuss now. First, let us consider an isolated positive charge. If we have a positive charge, the electric field is always directed away from the positive charge as far as the positive charge is concerned. And for the negative charge, the direction of the electric field is always towards the negative charge, here away from the positive charge. That point you have to note. Then, electric field due to a system of charges. Now we have seen for a single point charge. When we have more number of charges, already we have discussed the same thing in the force, Coulomb's force. Here we are going to discuss about the electric field due to a system of charges. When we have Q1, Q2, Q3, Q4 up to Qn, n number of charges in space or vacuum, how to calculate the electric field or total electric field at a point P, that we have to discuss here. Look at the diagram. Here we have 1, 2, 3, 4. 4 charges we have. Here Q1, Q2, Q3, Q4. Let us choose a point P. From the point P, Q1 is at a distance R1P, R2P is Q2, and Q3 is at R3P, and Q4 is R4P. All the distances are corresponding to the charges. So every charge is a positive charge. Therefore, at a point P, due to the positive charge Q1, you have a field E1, and due to Q2, you have E2, all directed outwards. And Q3, here we have Q3, and it is E3 is the field, and for Q4 we have E4. And now you have to use the superposition principle. And geometry says that if you want to calculate the resultant between E1 and E2, you can use the vector addition method, and you have to extend this process for the all the electric fields, and that will give you more difficulty. Okay, so you have to, everywhere you have to use a vector algebra, parallelogram law, triangular law, everything. So instead of doing that, we can apply this called a superposition principle. Okay, how to write the expression for electric field E1 due to the charge Q1 at a point P is obviously E1 vector is equal to 1 by 4 pi epsilon naught Q1 by R1 P square, R1 P cap. This is our general convention, because we know what is electric field due to a point charge. Okay, so 1 by 4 pi epsilon Q by R square into R cap. That is what we have discussed in the previous slide. Okay, based on the same thing, we have written the electric field E1 for the corresponding charge Q1, and for electric field E2, that is due to the charge Q2 at a point P, we have written as E2 vector is equal to the same thing. In the place of Q1 we put Q2, in the place of R1P we put R2P square, and corresponding unit vector R2P. Now we extend the concept for n number of charges. Similarly, we can write expressions for electric fields E3 vector, E4 vector, up to En vector we can write for all the charges available. So the total electric field at a point can be written as, according to the superposition principle, you can write E vector is equal to E1 vector plus E2 vector plus E3 vector plus etc. plus En vector. Is it clear, students? Fine. Okay. Now you sum it up all the quantities, and common term is 1 by 4 pi epsilon naught. Then you add all the quantities, Q1 by R1 P square R1 P cap plus Q2 by R2 P square R2 P cap plus etc. plus Qn by R and P square into R and P cap. This is the net electric field for us. And this also rewritten as in a simplified form by summing up all the quantities. 1 by 4 pi epsilon naught. You cannot take charge common, so that sum over I is equal to 1 to n qi divided by RIP square into RIP cap. When you substitute the index values, you can get the previous equation. Now let us discuss about electric field lines. How to visualize the electric field? We cannot see the electric field, but we can explain the properties of the electric field with the help of the field lines. Electric field is represented by field lines. They start from always positive charge and end negative charge when we have both positive and negative side by side. But they never form closed loop, which indicate the existence of isolated static charge. You understand my point? It starts from positive charge and terminates and ends with the negative charge. It will not return back to the positive charge. It does not form any closed loop. So this is the reason we have isolated positive charge and isolated negative charge in space. Monopole is possible. They never intersect. That is another important point. So suppose when they intersect, let us assume that at a point, if they intersect each other at a single point, we should have two directions, which is not practically possible. That's why we can confirmly say that no field lines will intersect each other at a point. They are continuous in electric free region. So no breaks, no breakup, they are continuous lines. In the case of single positive charge, starts from the charge and travels towards the infinity for a isolated positive charge. For isolated positive charge, the field lines will start from the positive charge and will go on continuously up to infinity. In the case of negative charge, field lines may come from infinity and can end with negative charge. Now let us look at some of the cases. We have positive charge here and we have negative charge. We have already seen that the positive charge produces electric field and the field lines are directed outwards, and as far as negative charge is concerned, the field lines are directed towards the charge. If we have positive and negative side by side, you can observe here the field lines start from positive charge and ends with the negative charge. And look at this picture, there is no field line start from negative charge and ends with the positive charge. So it does not produce any loop. Okay, that is a very important point you have to keep in mind. And look at the vector representation of the electric field lines. Here, see the positive charge, see the arrow mark. Nearby the positive charge, the arrow length is longer one, and if you go on, the length of the line is going on decreasing. The reason we know that electric field is inversely proportional to square of distance. That is represented when we go away from the positive charge, automatically the field strength is going on decreasing. That is represented by this line segment is going on decreasing. And this diagram for the positive charge, if there is no if you have charge free region, the lines are continuous. That can be understood from this diagram. Okay, next one more thing we have to know, electric flux. This quantity is very important quantity for us. What is electric flux? Electric flux is nothing but number of field lines crossing through a particular area. Suppose electric field comes here, you have a normal area, that is area is perpendicular to the electric field. So how many number of electric field lines are crossing through the given area which is kept normal to the electric field? That quantity is nothing but electric flux. Generally it is represented as phi. Phi is equal to, generally it is the product of, for a open surface you have electric field capital E and you have area, you just multiply E into A in the case of normal position. Okay, so when you have area which is normal to the direction of the electric field, you simply multiply electric field and area, you will get the electric flux. But when you have a closed surface, and this is the equation for us, phi is equal to integral over a closed surface E vector dot ds vector, or simply E ds cos theta, where ds is a small area element, and unit is Newton meter square Coulomb to the power of -1, because we know that electric field is equal to force by charge. So Newton by Coulomb. So NC power -1. Area is m square. So that is the unit for the electric flux. Okay, this is what I have said. So here we have electric field, and now we have the area A. Area vector is perpendicular to the area, which is normal to the area. It makes an angle theta with the electric field. That's why we have generalized to one electric flux is equal to E into A into cos theta, because here the electric field is resolved into component. E cos theta is along the area and E sin theta is perpendicular, which is along the surface. So this will not do anything to the electric flux. So we will consider only the cos component of the electric field. So therefore you can write it as, or you can resolve the area into components. So either way is possible. So in this case electric flux is equal to EA cos theta. So now if you specifically, if you want to say, if the area is perpendicular to this electric field, so this theta becomes 0. So in that case cos 0 becomes 1. So you will get electric field into area, that will give you the flux. And now look at this. This is a arbitrary surface. In the arbitrary surface we have small incremental small surface which is nothing but dA. Electric field is upward direction, it makes an angle theta. In this case you can write it as integral not over a closed surface, it is an arbitrary surface E cos theta into dA. Now come to the another case. This one is a closed surface, it is not an open surface, it is a closed surface, and if you follow the same thing you can write it as integral over a closed surface E vector dot dA vector or ds vector. So that is only the notation difference, either ds vector or dA vector doesn't matter. And this quantity is equivalent to q by epsilon 0, which was shown by Gauss's, okay, Gauss. So that is called a Gauss's law, and we will discuss later about the Gauss's law. That quantity can be easily determined for any closed surface. Okay, you got it? Yes. Okay, fine. Next we come to another topic called electric dipole. So we know that di means 2. Okay, an electric dipole is a pair of equal and opposite charges plus q and minus q separated by a distance 2a. You have positive charge and you have negative charge, which are magnitude wise equal, and they are plus minus charges separated by 2a distance. Why we have to choose 2a distance? For our mathematical convenience. And it has dipole moment p vector, which is always directed from minus q to plus q. The direction of the dipole moment is minus q to plus q. We have to keep in mind this point. Yes. The p vector is equivalent to general formula is there, but I have given you the result. Any one of the charge in the dipole, magnitude of the charge, positive, negative, you don't bother about the sign, you take the magnitude q multiplied by the distance between the charges and you put the unit vector, that will give you the dipole moment vector, which is, as far as the dipole is concerned, which is always directed from minus q to plus q. You take this one. Here we have, suppose if you take positive charge here and positive charge here, and this diagram you can imagine for water molecule. So in water molecule we have H2O. Here one H plus, here one H plus. So here one positive charge, here one positive charge. So here we have the center of mass for the two masses. And here oxygen. So here we have the mass. Okay. So this is negative charge and this is positive charge. This we have a small distance, let maybe 2a. Okay. So this will constitute an electric dipole. The direction of the electric dipole moment is negative charge to positive charge, which is shown by green arrow mark. Okay. And now another diagram is here. This is positive charge, this is negative charge. Distance between them are here. But if you write it as 2a, this dipole moment is q. Any one of the charge I have taken, multiplied by the 2a. So that will give you the magnitude of the dipole moment. Its unit is Coulomb meter, right? Okay. Now we have come to the important concept. This question is very, very important. Field along the dipole. How to find out the electric field due to the dipole. We already familiar with the dipole, electric field due to a point charge. That we know. Here we extend the concept to the dipole. Field along the dipole. Let us consider a dipole of having charges plus q and minus q separated by a distance 2a. P is a point on the axis at a distance r from midpoint of the dipole. Now we have two electric fields. One is due to positive charge and the another is due to negative charge. It may be E plus Q, E minus Q, or the electric fields due to plus Q and minus Q respectively. Now we have to find out the total electric field. P vector is a dipole moment which is always directed from minus Q to plus Q. These things we have to write as notes. Okay. Now see the diagram. Here we have a dipole, right? This is positive charge plus Q and this is negative charge minus Q, which is separated by 2a distance. Am I right? This is midpoint. Okay. So dipole moment vector P vector is going from minus Q to plus Q. We choose a point along the axis of the dipole at a distance r from the midpoint. Okay. Here we have two electric fields. One is E plus Q and another one is E minus Q. Look at this arrow marks. This length is larger one. This length is shorter one. Okay. Why this is shorter? E minus Q is due to the negative charge. The distance is more. Therefore, the field due to the negative charge will be less. Whereas E plus Q is due to the positive charge. The distance between the point and the positive charge is lesser. Therefore, the field strength is much more high. So, definitely the electric field due to positive charge will dominate here at this point P. Let us check. For points on the axis, now let us first write the electric field due to positive charge. Very simple, 1 by 4 pi epsilon 0 q by the distance square. So what is the distance between the point P and positive charge? That we have to note down here. See, this distance from the midpoint to point is, what is that? It is r. But this is midpoint, therefore this is a, this is also a. So from the whole distance r, you have to, because we have to calculate the distance from this point to this point. Therefore, you have to subtract this. R minus A is the distance for calculating the electric field due to positive charge. To calculate the electric field due to negative charge, you have to add A with R. So, you will get R plus A in that expression. Let us see here. Okay. So, for electric field due to negative charge, we have R plus A whole square. And look at the unit vector. This vector is P cap is acting towards left hand side, which is along the direction of the dipole moment vector. Whereas in the case of electric field due to negative charge, which is opposite to the dipole moment vector. Dipole moment vector, if you see the diagram, dipole moment vector is towards the left hand side, towards left it goes, or towards negative x-axis. Whereas the electric field due to negative charge is towards the positive x-axis, which is opposite to the dipole moment vector. That's why I have written with the minus. Okay. To find the total electric field, E vector is equal to E plus Q vector plus E minus Q vector. So together we are having this equation. 1 by 4 pi epsilon naught Q by R minus A whole square P cap minus, because we have minus here, we have plus here, plus into minus, minus 1 by 4 pi epsilon naught q divided by r plus a the whole square into p cap. Next, simply mathematical simplifications. You take the common term q by 4 pi epsilon naught. So you will get 1 by r minus a the whole square minus 1 by r plus a the whole square into p cap. Then LCM, r plus a the whole square minus r minus a the whole square divided by r minus a square into r plus a the whole square. Expanding this, you will get, according to a plus b the whole square, you will get r square plus a square plus 2ra, r square plus a square minus 2ra. You just multiply the minus inside, you will get minus r square minus a square plus 2ra divided by, here you will get r minus a into r plus a the whole square, because a square b square is nothing but ab the whole square. So therefore you can write it as r minus a into r plus a the whole square. So that some terms are cancelled in the numerator, plus r square minus r square plus a square minus a square. So ultimately you are getting 4ra only. But in the denominator, according to the a minus b into a plus b, you will get r square minus a square the whole square. So 4ra in the numerator, and in the denominator you will get r square minus a square. When r is very greater than a, let us assume this. If you choose a point P at a larger distance from the dipole, and you can neglect the quantity a square, because a is very small, a square is very small, which is negligibly small. So you will get r square to the whole square, you will get r power 4. And if you cancel one r, you can get this quantity 4a divided by r cube. And rearranging the equation up to this is enough as far as your textbook is concerned, but we will little bit extend this. 4qa is nothing but 2 into 2qa. Am I right? You know very well 2qa is the dipole moment. Okay, magnitude of the dipole moment. So therefore you can write this term as, am I right? So this quantity 4qa is nothing but what? 2 into 2qa. What is 2qa? 2qa is dipole moment. Okay. So 2p by r cube into p cap. So I don't pronounce 1 by 4 pi epsilon every time, it is there. Okay, you just note down. Okay. Now 2 p cap. P cap can be written as p vector. So this is the, eventually we are getting this term 1 by 4 pi epsilon naught 2p by r cube. So this is the final expression for the electric field at a point due to the dipole along the axis at a distance r from the midpoint of the dipole. Okay. What do you understand from this? Electric field is inversely proportional to r cube. Okay. As far as the point charge, single charge is concerned, this electric field is inversely proportional to r square. Whereas in the case of dipole, the electric field is inversely proportional to r cube. And another thing is, when you have more dipole moment, the electric field is also much more high. It is directly proportional to the dipole moment also. So this is the discussion for the electric field along the axis of a dipole. So you go through all these things, dear students. If you have any doubt, you just write in the comment box. I will try to clarify. And wait for the next video. I will meet you with another interesting things in the next video. Keep watching, and I request you all, my dear beloved students, subscribe the channel Wisdom in Physics. Keep watching. Thank you.